Hey guys, welcome back to Data Products. This is part 4, I believe, of our exploratory data analysis journey. In this one, we're going to do some probability plots and maybe some Shapiro Test to see if our data is in a normal distribution, if we have time. Otherwise, that'll be in part 5. So with that, let's go ahead and get right on into it. Okay, so let's do some probability plots. So first thing we're going to do, let's do library ggplot2, library Tiger stats, and we're going to we will use the probability plot function, and their output dnorm density function of the normal distribution. Using the density, it is possible to determine the probability of events or, for example, you may wonder, what is the likelihood that a person has an IQ of exactly 140? In this case, you would need to retrieve the density of the IQ distribution at value 140. The IQ distribution can be modeled with a mean of 100 and a standard deviation of 15. The corresponding density is... Actually, we're going to change this. We're going to change this to BMI. To a BMI of exactly, and we'll say blank. Oops. We're going to stay on. We don't need any more data sets. So let's just use our BMI data, because we got it. BMI.mean is the mean of obesity. And we have BMI and the obesity data set here. And then the BMI.standard deviation is SD for standard deviation, obesity, BMI. Alright, so we can get those values. So you see over here we have our standard deviation of 6 and our mean BMI of 30.6. Let's create a plot of our normal distribution. So, what's going on here? There we go. BMI.dist is going to be p-norm. Oh no, sorry. D-norm. Obesity BMI. Mean equals BMI.mean. SD equals BMI.SD. BMI.dataframe is going to be data.frame. BMI equals obesity BMI. Density is going to equal BMI.dist. And then ggplot BMI.dataframe. AES equal, or no, aesthetic x equals BMI. We're going to plot the BMI. Y equals density. And I'm actually going to break this off down here because we're plotting. It's kind of a separate thing. and then we're going to do genome point. Okay, so we made our distribution with the D norm where we gave it the mean and the standard deviation, and then we made our data frame, and then we plotted it. So here's our distribution of body mass index based on a standard deviation and a mean. Okay, this gives us the probability of every single point occurring. Now let's use the p-norm function for more info. Alright, so bmi.dist is p-norm, obesity, BMI, mean equals BMI.mean, SD equals BMI.SD. BMI.dataframe now, we're going to save over it and use the p-norm instead. BMI equals obesity, oh, we should capitalize that, obesity, $, BMI, density equals BMI.dist, and then ggplots, BMI.df, aesthetic, x equals BMI, y equals density, and genome point. Okay. Density. 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 There we go. Okay, so this is just a p-norm. So it's just a different way to show the distribution where we have our BMI. This is essentially 0% of them are down below 20, below 10, I guess you'd say, no, below 5, and none of them are above 53 or something like that. So it depends how you want to. So this just depends how you want to display it, really. What if we want to find the probability of the BMI being greater than 40 in our distribution? pp underscore greater. We're going to make a function where we give it x and paste, paste rounds 100 times our p-normal distribution where x mean equals 30.66339. That was what we, let's put this in our brackets so we can see our stuff here. All right, so our mean is what our mean was. I just got that number from right up here. Our SD equals 6.09818. You can give as many digits as you want. SD, we did that. No, we gave it the SD. Lower tail equals false because we're only looking at stuff greater, so we don't want to see the lower. We want to see the upper. And then we want 2, and then we want quotation, percent quotation, and then our function ends. So then let's do pp greater 40. Let's see what it gives us. So the probability of the BMI being greater than 40, 6%, 6.29% are BMI is greater than 40. So anything over here on the graph. And so when I added this percent thing, It just, so when we print it out, it adds a percent sign here. That's all that's doing. And the 2, all that's doing is say go to 2 decimal places. Oops, sorry, the percent here, I was doing it on my notes. So the percent, that just says add a percent sign, and the 2 says go to 2 decimal places. So if I change this to 3, you see we have 3 decimal places. I like 2. Perfect. Okay. So now, what about the probability that a BMI is less than 40 in our population? So we can do that too. Pretty simple. You might say, well, it's easy. We just subtract 100 or 6.29 from 100. Well, that's true, but we can also make a function for it. So pp underscore less is a function where we give it x and paste round 100 times 1 minus p norm x mean equals, we'll say 30, and then SD equals 6, just so we don't type in all that stuff. Lower dot tail equals false, 2, and then we'll give it a percent sign so it prints out a nice percent sign for us. And then we'll close off our function, close off our R block. I have to call the function pp less, and then give it 40. Not 60, not 50, 40. There we go. So 95.22%. And this is, these don't equal because I changed these numbers, right? So let's see it. If I want to give them this number and this number, let's try it again. There we go. So those 2 numbers equal out. Perfect. Okay. What if we want to find the area in between? Let's create a function for that. So p norm gc 40 sorry, c 20 40, so we've given it our 2 regions, and we have the region equals between, mean equals, we'll give it this number just so we can stay consistent. SD equals, we'll give it this number, and then we'll say, let's say graph equals true, and then close this out. P norm GC, why? Oh no, let's see, forget a library somewhere. Did I run? I forgot to run Tiger Stats, the package at the top. Okay, so if you run it, you should have this. So this pnorm GC is part of the Tiger Stats package, and it will give you a given the mean and the standard distribution, it'll give you, or standard deviation, it'll give you this distribution, and you can give it two values, and then the region between, and it'll say, okay, we have our mean or standard deviation, and 89.69% or 0.8969 fall between 20 and 40 on this distribution. Okay, let's get back on track here. So you can also do so you can also use this for like the normal stuff. So actually I'm going to go up here. Let's do pnorm GC. So this is when we were looking for less. We'll do 40 region equals below. I'm sorry, I'm jumping around here. Mean equals, we'll grab our mean, our standard deviation up here, put it down here, and then we'll say graph equals true. So we're going back up to our less BMI less than 40 section here, and I'm going to add this. Maybe below is going to be lowercase. There we go. So now you can see that we get this nice graph from this Tiger Stats, right? And again, you can do the same thing if we do it. So now I'm going to go back up again to our code where we find a BMI greater than 40. So I'll just change this to above and run that, and you can see we get a nice graph for that too. Okay, so now let's keep going. What if we want to know the quantiles? Let's use the pnorm function. We need to assume a normal distribution for this. What BMI represents the lowest 1% of the population. So instead of asking a question starting with a BMI number, what if we just want to know the percents, right? So we say, okay, what's the lowest 1%? Well, what we can do is, actually, why did I say I'm going to use Q? Why is this? There we go. Okay, so Q norm 0.01, so 1%. Mean equals, I'm just going to paste this mean standard deviation stuff again. Oh, crap. Oh man, I'm kind of in a blender here. Alright. Mean standard deviation, and then lower tail equals true. Alright, see it. Typo, gotta get rid of this M. Okay, what? Oh gosh. Alright, so if you have a BMI of 16.47, you are in the lowest 1%. 16.47 or lower, you're in the lowest 1%. So pnorm allows you to give it like a percentile, and then get the value for that percentile. Alright, what if you want a random sampling of values within your distribution? Subset is the function we can use, or we'll call it subset. We use rnorm 50. Say we want 50 values from our distribution. Mean and standard deviation. And then hist of subset. And again, I forgot to put this in our brackets. So we've done this before, right? We used rnorm. And so if we wanted to just get a samples from a random distribution, we use our norm. We give it the number we want, and then we just give it our mean and our standard deviation from our own distribution we have above. Pretty easy, huh? And so if we let's do this again with the larger sample size. So subset 2 is our norm. We're going to give it 5,000. And then I'm going to do my standard deviation and mean, and then hist subset 2. So you can see you get a much nicer bell-shaped curve. This one, because we had such a small sample size, it doesn't really mirror the distribution, right? It's kind of skewed because it's all random. But this one, the higher the sample size, so if I did, let's do 50,000, you get the larger your sample size, the more normal your distribution will look. All right, 21 minutes, we can rock through this. Shapiro Wilk test. All right, so now we know how to generate a normal distribution. How do we tell if our samples, like we did just now, a random sample, came from a normal distribution? So we're going to look at, this Shapiro test. So if we run this, I gotta move myself up. So as you can see here, the Shapiro test performs the Shapiro-Wilk test for normality, what it does, you just have to give it a numeric vector of data values, and that's it. It's pretty easy. Here's the source if you want to read the paper about the Shapiro-Wilk test. Multiple sources. Let's put me back down. Oh man. Golly. Okay. Alright, so we're going to do Shapiro test. Actually, I'm just going to do this. Alright, so for the Shapiro-Wilk test, we do Shapiro test. Obesity charges is what we're going to use. We're going to end 1 through 5. So we're doing just 5 values, our first 5 from the charges to see if they're from a normal distribution. And you can see here with a small sample size, we would reject the null hypothesis that the samples came from a normal distribution because our p-value is higher than 0.05, right? We can increase the power of the test by increasing the sample size. So let's try this again. So it all depends on how big of a sample you give it, right? So Shapiro test, obesity charges, and let's instead give it 1 through 1,000. Okay, so once we give it 1,000 data points instead of 5 data points, you can see that yes, the distribution of charges is a normal distribution. So it all depends. Garbage in, garbage out is my old advice used to say. So if you are putting in not enough data for the test to work, then you're going to have a bad time. So, so always try to include as much data as possible in these things to see if it's a normal distribution. Okay, so now let's check out age. So Shapiro.test, obesity, age, I'll give it 1 through 1,000. Oops. Let's see what happens here. Normal distribution makes sense. And lastly, BMI. All right, so let's do Shapiro.test, obesity, BMI, 1 through 1,000. And that one, see, it's less, well, I shouldn't say less, it's still significant. The p-value is much less than these other ones. So let's try it with 500. See, if we give it 500, it's not enough to give us significance because the data it's borderline normally distributed, I guess. So yeah, so you can play around with that, play with different numbers, so you can see that, you know, depending on the sample size that you give it, will determine whether or not it's significant or not. So this is a tool, you know, to kind of tell you, because you need to know if your data is normally distributed in order for you to determine what type of regressions or t-tests or whatever type of statistics you're going to do on your data. You need to know if it's normally distributed or not, because certain tests have rules, right? And so it's like just a linear regression needs normally distributed data. And so if you're using non-normally distributed data in a normally distributed statistical test, it doesn't, your conclusions aren't valid because you're kind of, you know, not using the test correctly. So that's it. Excuse me. So that's it for this video. We have maybe 2 more in this data analysis series, or preliminary data analysis series. We're going to do some time series data, and then we're going to do another outlier check. And then I think we're done. And then we're moving on to other things. So with that, if you're watching on YouTube, hit like, hit subscribe. I appreciate it if you would do that. And stick with me. Plenty more content to come. And I will catch you guys in the next one.